Hello, my name is Daniel Simpson, and I will be your guide for this algorithmic excursion. Welcome to episode 1 on the Change-Making Algorithm, Dynamic Programming Edition. You are a human waiter working in the popular space diner The Tangy Tentacle, which is known for its fine cuisine. This is the best job you could land after you flunked out of your degree program at the Neptunian University of Quantum Computing. Business has been booming lately, so the boss hired a new robot to help with serving and cashiering. You've barely been able to keep up with the work yourself, so you're excited for the extra help. However, 10 minutes into the robot's first shift, you hear an angry glorp from a frequent customer. You turn around and see that the robot has made a mistake and has given the customer change for 200 credits in 2 credit coins. This simply won't do. You quickly give the customer change in a more appropriate denomination and take the robot to the back room to teach him how to calculate change properly using the dynamic programming version of the change-making algorithm, one of the few things you were good at while you were still in school. You use an example scenario in which the robot must make change for 12 credits using the set of 1, 2, 3, and 6 credit coins. Given an amount, in this case 12, and a set of coin denominations, in this case 1, 2, 3, and 6 galactic credits, you can solve for the least number of these coins needed to achieve the amount. So step 1 is to make an array of size n plus 1, where n is the amount you seek to make. Step 2 is to set the first element of that array equal to 0, and step 3 is for each increment of index marker I, you choose the minimum value of f of I minus each coin, add 1 to it, and set that number as the current index of I. You then increment I and continue until I passes the end of the array. Alright, so given the amount n is 12, the denominations m are 1, 2, 3, and 6, and the index variable initialized to 0. Step 1 is to create an array of size n plus 1, and since n is 12, our n plus 1 is going to be 13, so we now have an array of 13 elements, which is currently empty. Step 2 is to initialize f of 0 to 0, which we have done so here. Step 3, which is the repeating step, it was a bit hard to explain in English, but it's easier to see worked out. F of I is equal to the minimum of whatever comes out to be the minimum of this set. So f of I minus 1, f of I minus 2, f of I minus 3, and f of I minus 6. And then you add 1 to that at the end. So for the first one, I equals to 1. So f of 1 will equal the minimum of this set. So if I is 1, 1 minus 1 is 0. We can't use this one because 1 is less than 2. So this would give us an index that's out of range. The same thing here. 1 is less than 3. That gives us an index that's out of range. And 1 is less than 6, which gives us an index that is out of range. So, well, what is at this 0? 0 represents the index of the value you're looking for. So f of 0 contains 0. So this turns out to be the minimum this time. Add 1 to it because of this plus 1, and that equals 1. So we then set f of 1 equal to 1, like we did here. We then go through and do this for all values of I. So I equals 2, so f of 2 is equal to the minimum of f of I minus 1, f of I minus 2, f of I minus 3, or f of I minus 6, with plus 1 added at the end. So 2 minus 1 is 1, 2 minus 2 is 0, 2 is less than 3, so we can't use this one yet, and 2 is less than 6, so we also can't use that one yet. So, well, what's at this index of 1 that this is representing? Well, f of 1 contains 1, okay? Well, what's at this 0? Well, f of 0 still contains 0. That's never going to change again. So, since this, we compare the answers we get across here, and this one's the smallest, which is 0, so we then take this plus 1, add it to it, get 1, so then we set f of 2 equal to 1, like we did here. The next one is I equals 3, so f of 3 is equal to the minimum of f of I minus 1, f of I minus 2, f of I minus 3, or f of I minus 6, with 1 added at the end. So 3 minus 1 is 2. 3 minus 2 is 1. 3 minus 3 is 0. So we can use this one now because we're up to 3. But 3 is still less than 6, so we can't use that one yet. So what's at index 2? F of 2 contains 1. What's at index 1? F of 1 contains 1. What's at index 0? F of 0 still and will always contain 0, which in this case we compare the 1, and the 0. 0 is the smallest, so we want to add this 1 to 0, and we get 1. So f of 3 is equal to 1, as you can see here. I equals 4, so f of 4 is equal to the minimum of f of I minus 1, f of I minus 2, f of I minus 3, or f of I minus 6 with a 1 added at the end. So 4 minus 1 is 3, 4 minus 2 is 2, 4 minus 3 is 1, but again, 4 is still less than 6, and that gives us an index that's out of range, so we can't use that. So what's at f of 3? F of 3 contains 1. What's at 2? F of 2 contains 2. What's at 1? F of 1 contains 1. Now comparing these, we've got 2. You see this one and this one. They're both the smallest, but it doesn't matter. We just need the smallest value, not which index it's sitting at. So for the sake of clarity, I'll choose the one at the end. So the value we have is 1. We add this 1 to it, and we get 2. So f of 4 is equal to 2. We set it equal to 2 in the array and increment I. So I equals 5 now. F of 5 is equal to the minimum of f of I minus 1, f of I minus 2, f of I minus 3, or f of I minus 6 with 1 added at the end. So 5 minus 1 is 4, 5 minus 2 is 3, 5 minus 3 is 2, and 5 is still less than 6, so we can't choose that one because that's going to give us an index that's out of range. So, well, what's at 4? F of 4 contains 2, 3, f of 3 contains 1, 2, f of 2 contains 1. And again, we've got 2 that are the same, but it doesn't matter because we just want to know what that smallest value is. So we take this 1, add the 1 to it, so we get 2, and set f of 5 equal to 2, and increment I. Okay, so now we're at I equals 6. Well, f of 6 is going to equal the minimum of f of I minus 1, f of I minus 2, f of I minus 3, or f of I minus 6 with 1 added at the end. So 6 minus 1 is 5, 6 minus 2 is 4, 6 minus 3 is 3, and now we can use this one because we're up to 6. 6 minus 6 is equal to 0. So what's at 5? F of 5 contains 2, 4, f of 4 contains 2, 3, f of 3 contains 1, or 0, f of 0 contains 0, which is the smallest in this set. We add our 1 to it, and we get 1. So f of 6 is equal to 1. So I equals 7. F of 7 is equal to the minimum of f of I minus 1, f of I minus 2, f of I minus 3, or f of I minus 6 plus 1. So 7 minus 1 is equal to 6, 7 minus 2 is equal to 5, 7 minus 3 is equal to 4, and 7 minus 6 is equal to 1. So what's at this index 6? F of 6 contains 1, f of 5 contains 2, f of 4 contains 2, and f of 1 contains 1. And since this is the smallest value in this set, even though it occurs twice, it's the smallest value, we will choose it, add our 1 to it, so it equals 2, and set f of 7 equal to 2. So I equals 8. F of 8 is equal to the minimum of f of I minus 1, f of I minus 2, f of I minus 3, or f of I minus 6 with 1 added at the end. So 8 minus 1 is 7, 8 minus 2 is 6, 8 minus 3 is 5, and 8 minus 6 is 2. So what's at index 7? F of 7 contains 2, f of 6 contains 1, f of 5 contains 2, and f of 2 contains 1. Now we have our 1 occurring twice, but that's okay. We just want its value. So we choose 1, add 1 to it, and get 2. And we set our f of 8 equal to 2 in the array, and increment I. I now equals 9, so f of 9 is equal to the minimum of f of I minus 1, f of I minus 2, f of I minus 3, or f of I minus 6 plus 1. And so 9 minus 1 is 8, 9 minus 2 is 7, 9 minus 3 is 6, and 9 minus 6 is equal to 3. Well, what's that? F of 8. F of 8 contains 2, f of 7 contains 2, f of 6 contains 1, f of 3 contains 1. And you see we have our smallest value. It doesn't matter which one we choose. And we're going to add 1 to it, and we come out with 2. So f of 9 is equal to 2 in the array. So at I equals 10, f of 10 is equal to the minimum of f of I minus 1, f of I minus 2, f of I minus 3, or f of I minus 6 plus 1. So 10 minus 1 is 9, 10 minus 2 is 8, 10 minus 3 is 7, and 10 minus 6 is 4. So at f of 9 we have 2, f of 8 we have 2, f of 7 we have 2, and f of 4 we have 2. They're all the same this time, but it doesn't matter because we just want the value. So 2 plus our 1 is 3. So f of 10 is equal to 3 in the array. Now, at I equals 11, f of 11 is equal to the minimum of f of I minus 1, f of I minus 2, f of I minus 3, or f of I minus 6 with 1 added at the end. 11 minus 1 is 10, 11 minus 2 is 9, 11 minus 3 is 8, and 11 minus 6 is 5. And so the smallest value we're going to get here is going to have to be 2. Yes, 2. And so we'll then add our 1 to it and end up with 3. So we set f11 equal to 3. And the last one, f of 12, is equal to the minimum of f of I minus 1, f of I minus 2, f of I minus 3, and f of I minus 6 plus 1. So 12 minus 1 is 11, 12 minus 2 is 10, 12 minus 3 is 9, 12 minus 6 is 6. At f11 we have 3, at f10 we have 3, at f9 we have 2, and at f6 we have 1. 1 is our smallest number in this set, and we add our 1 to it, giving us 2. So f of 12 is equal to 2. That means that the, well, not just in this case, but in every case, the last number in your array will be the number of coins that you can make this change with. So if you remember, the amount of change that we needed to make was 12. So if we go back down here, we know that we can make 12 using 2 coins. Oh, that's a bad one. I can't just let that stand. Okay, so looking at this, we can then, this is the answer that the algorithm gives. But using intuition, you can find out, well, what are those 2 coins? The coins that you will use will be denoted by the value, the index that gave you the smallest value in this last test. So it's not this one because that was a 3. It's not this one because that was a 3. It's not this one because that was a 2. It's this one because it was a 1. And keep in mind that it is possible to have multiple ways to get the final intended amount at the end. So in this case, if we have 2 of these 6-piece coins, I'm not even going to try and write that, then we'll end up with 12. But say we had say it was a different problem and we had more than one minimum value here. That doesn't mean that each one of those will be 2 of exactly that. It will mean that every one that was the smallest value could be, in some combination, the smallest, the greatest denominations that you could use to make the sought change amount. This algorithm is one of the dynamic programming methods, so it trades space efficiency for time efficiency. It has a time efficiency of big O of mn, where m is the number of denominations and n is the amount. It has a space efficiency of big theta of n, because we created the array to help with computing. Given this new information, the robot is able to perform well and makes your life a lot easier. The end.